So, yeah, I wanted to talk about a little bit about my experience in using DLLs with LabVIEW. It's come up a few times recently for me. So I've been doing a lot of work on kind of new product development. So working with R&D engineers in developing new measurement systems. And there's been kind of 3 different cases for different reasons where it's been useful to look at using DLLs rather than doing everything in pure LabVIEW. So this is a little bit of a, I'm not going to go into great technical detail on how it works with LabVIEW. I'm going to skip over that fairly lightly, but what I wanted to do is just talk about my experience with them and why I felt that that was the way to do it. And hopefully that will either make you go, oh, actually, yes, that might help us here, or no, I never want to touch them. Thank you very much for convincing me. Both responses are perfectly valid. So why would you do it? I've had 3, like I say, 3 different cases recently. The first one, which is probably the most common one I've heard people talk about, is performance. So in this particular case, it's actually a case study I've put up recently on my site with quantum detectors who develop like a particle detector system. And we needed to get the performance up from about 300 frames per second to 2000 frames per second. And LabVIEW did pretty well. LabVIEW got us up to, I think, about 800 or 1000, but I just couldn't make it go any faster. And, you know, it's admirable for what it was doing, but we had to go to C so that we could use some of the more advanced capabilities of processors, basically. The biggest performance restriction I've seen in LabVIEW is there's like additional data processing instruction sets that are now available, but LabVIEW is still won't use them until it's still based on the old vector instructions. The SSE2, I think, is as far as it goes, whereas now there's AVX and AVX2, which are much wider registers, which means if you've got lots of repeated processing, like dealing with big arrays, it can be done a lot faster. So that's the biggest case, and I guess probably the most obvious case, and probably the one will be seen the most. But I've also seen a couple more. One is unsupported features. This might depend a little bit more on other capabilities you already have. In my case, I was writing a command line application in Rust, and I wanted to get some data from my LabVIEW application to that, and quite a lot of data. So basically JSON was too slow. I knew that there were these other binary formats out there, but there's nothing supported for that in LabVIEW. So I created a DLL that LabVIEW could call to kind of access those capabilities from Rust. The other one that I'm experimenting with still, but I quite like, is common processing across languages. So more and more projects I'm doing have a data science element. And so that tends to mean Python. And often there's like processing on the embedded system that we want to replicate in the Python environment. So by using a common language like C or Rust, I can write the algorithm once, wrap it for LabVIEW, wrap it for Python, and we know we're using the same processing techniques. So those are the reasons that I've found lately to do this. If you haven't used it in LabVIEW, it basically is like a special node. Let me check if I can get this up. Can you all see some LabVIEW code now?
Yes.
Perfect, thank you. So this is the function node for calling a DLL.
I'm going to tell you off for not using show names.
Yes, actually, that's a good point. I'll put it on so you can see. Is it names like that?
Yeah.
Actually, that isn't what I was
thinking. It helps reading a lot if you actually name things correctly.
Yeah. No, I like that actually. I thought you meant just the label actually when you first said it in my head. I didn't realize you could do that one. Nice. Right, have a play with that. Yeah, so this is basically a dynamic node. So one of the challenges with DLLs is they're not self-describing in any way. So you have to point it to the DLL you want to call, and you have to select the function name. It will tell you what the function names are, but it doesn't tell you what the parameter list is. So you have to come in here, define all of this, and then you get this node on your block diagram. So that's the basic structure for interfacing to this. And that lets you go to any language that can produce a C style, some of them call it FFI, foreign function interface, or ABI, application binary interface, I think. Anything that says it can talk to C effectively, you can call it through that. And so with that in mind, I guess the reason for talking about this is what I found the hardest was the memory management. So the actual kind of runtime execution, it kind of makes sense already, right? You've got that node and it works with data flow, just like the rest of LabVIEW. When all the inputs are ready, it'll call a function and output them. The hard bit is knowing how and what to do with the memory that's being used. And the reason for that is you have some parallel systems going on. So LabVIEW has its own memory manager, which is used to manage all the buffers that it needs to put memory behind the wires that we're using. And C++ use their own memory manager. Generally speaking, it's a function called malloc, which will do a dynamic allocation for you when you want it, and free, which is what returns that memory back to free it on the heap, is what they call that. And so LabVIEW and C are talking to each other, but behind the scenes there's these other two systems, and if you need to make sure that the memory is being managed, and it's done obviously in LabVIEW. Normally it's completely implicit. You don't see it happening. You don't have any direct control over it. It just happens. Whereas in C++, it's a bit more explicit. You put in your code, this is where we allocate memory, this is where we release memory. So deciding how to manage that is, well, I suppose it's deciding how to manage it and being very explicit with how to manage it is what I found was the solution to that problem. So I did this with what I would call is the easy way. So the DLL itself, in most of these cases, was handling a structure of data like a cluster. Moving clusters between LabVIEW and C is a pain in the bum, especially because in the performance use case, I had to make sure they had a certain memory alignment, for example, with the processor. So what I settled on is the DLL manages its own structures. And what I really mean by manages it, it decides when it's allocated, it decides when it's freed. And then builder methods copy data from LabVIEW to the DLL, and all LabVIEW sees of that data is a pointer, which is the memory address that C has allocated for that data. The careful bit is you must call free when you're done. If you don't call a function in LabVIEW to tell the DLL that you're finished with that structure so it can clean up memory, you will have a memory leak. For me, that worked because it was a very limited scope. In the scope of a whole application, it was one or two specific objects where I was using this. So, I could still have done it wrong, and I have done it wrong from time to time. But it felt possible to manage that without the risk of introducing too many memory leaks and not being able to track down where they came from. So at a simple level, this is what that looks like. So in this case, I have what I'm calling a data frame. So data frame has a waveform attached to it and multiple spectrum that we can attach to it. So it's purely a container for some of this data. So the new frame, this is where the DLL is going to allocate that. We give it the information we know it's going to need straight away anyway. And what it's going to do is it's going to allocate a space in its own memory for all of this data, and all we get out of it is a pointer. We can then use that pointer to manipulate it. So if we wanted to, if we needed to get information out of it on the LabVIEW side, we'd have to create another method to do that. Or in this case, I'm adding a spectrum as well to that frame. And then when we're done, we have to call a function that frees that data. And then really what I do for using it in LabVIEW is wrap it in a class. So there's a function for building it out. In this case, we add the spectrum as well straight away, and there's a function for freeing it. So the API starts to look like a Visa API or a DACMX API, where you just have to remember to call free at the end. Another interesting way to manage it, if you need a lot of these, I found was to do an allocation pool. So in the other project where it's about very high performance, what we did actually is at the start pre-allocate like 30 gigs worth of these images in that case. So I would call C to say, right, give me 30 gigs worth of images, return me all the pointers, and then in LabVIEW, I'd put those in a queue. And the reason that was helpful is A, it wasn't quite as clean cut in terms of where those images were freed or not. So what it meant is when something needed an image, it would dequeue a pointer and it would use that as its image. And when it didn't need it anymore, instead of calling free directly, it would return that pointer back to the queue. And then you call free on all the images at once, and I could inspect. I could say, well, I allocated 1,000 images. There's only 999 back in the queue. There's a memory leak somewhere. And it didn't fix the memory leak, but it meant that it threw a runtime error, which I could then debug. Yes. How much are people following that? Does that make sense? Especially with the kind of the memory balancing between these two. Yeah, I'm seeing a few nodding heads. I'll take that.
Yeah, I can say that I've worked with quite a few DLLs, and you really do learn a lot about how memory works.
Yeah.
And often because you get a DLL, it's not designed to be called from LabVIEW, and you have to adapt to it. And there's multiple different. Some DLLs are quite a joy to use. Some are a real pain.
Yeah. I mean, it's worth saying in this case, I'm writing the DLL as well, so I've done it in a way to make it as straightforward as possible to call. And yeah, I like. Yeah, I can't remember where I read it originally. It said it's the old play on The Usual Suspects. Says the biggest trick C ever pulled was to convince us that it doesn't have a runtime, because it does. It's just everywhere already, and exactly that. It has this memory model, which I've seen critics of C say it's a memory model based on how CPUs worked in the 70s, not how they work anymore. But exactly that, but it's very direct. It's, I have a chunk of memory with address and I can read and write from that until I've said I don't want it anymore. And it's quite fascinating. They're a very simple model, but very powerful, but gets very complex very quickly if you start trying to do a lot of clever things with it.
I've even had a DLL where the only way to call it was to pass it a LabVIEW array. It would take a pointer of it in one call, and then you have to pass that pointer to another call, which would fill it. And that meant, because LabVIEW doesn't know this, if you probe that array before the second one executes, you see nothing. But if you do it after the second one executes, you see it. And sometimes actually the indicator, the LabVIEW indicator for the array would show nothing, even though the array would pass out of the sub VI. So it was, I actually would have a big comment in an actual sequence structure to force it and to warn you that you're going to confuse yourself if you try and debug here.
Yeah. Do not look in the box.
I actually put down the standard comment is pointer weirdness.
Yeah. Did you have a question, Daniel?
Yes. Regarding wild pointers, if you work in the way you are doing it, have you experimented wild pointers?
Wild pointers. I don't think I've come across it. No.
So you never have like a LabVIEW crash because.
Oh yeah. Sorry, yeah, I've had LabVIEW crash. Yeah.
LabVIEW crash will be like a wild pointer. So that means that you are out of the memory of the context where LabVIEW is allocated, and that you are working with this DLL and you are allocated in the context of LabVIEW. It goes like out of that memory, and the OS crashes LabVIEW. Let's say that is what I mean with wild pointer. So my question is, working in the way that you are showing us, you have experimented it.
Yes, yeah. So this is far from foolproof. The important thing with the pointer, and especially when you're going back and forth to LabVIEW, is let me see if I can.
Because my question is
on here.
Something. Yes, I am. Imagine you have the experience because you've worked with this a lot, no? But have you tried, for example, pre-allocating like a big memory space in LabVIEW before doing like those operations? Or when did you experiment it having these pointers? When you allocate like big data or what?
Yeah. So, I mean, this really became necessary on, the first project where we did the performance, LabVIEW didn't see the data after the first step of acquiring it. Because we were, it was at the point where we were running up against like memory bandwidth issues on the old CPUs we were using. We were maxing out what a CPU could do with it, really. So in that case, we didn't want any kind of I found a note somewhere saying we cannot convert this data type; it takes too long. We're kind of struggling with that. So that was why we kept everything in C, because with C we could be really explicit about how the memory was managed. There's less chance of an accidental change. So that was what really forced me down that route. I think if you're reading data, so like, I did a function the other day, where it is just data processing. It's like, here's an array, spit out a number. So in that case, I wouldn't go through all of this. I would just pass in a LabVIEW array and just read it in C. It's really where these more complex types are just more difficult to manage with in LabVIEW, so I just avoid it. And that's why I push the pointers around, because the alternative is you can start to use clusters in LabVIEW, but you have to start worrying about things like the memory alignment in the cluster. It becomes very tricky, so it's easier to have it transparent. But you're absolutely right. So if you can imagine, I've got my LabVIEW code. Let me see if this will work. And I've got my C code. So the C code is going to create that pointer somewhere in time, and somewhere in time it's going to free that pointer. So the idea with this model is, C is going to create that. And actually, to be fair, what I should say, it's going to create that memory space. It's going to allocate that memory space for a certain amount of time. And then we're going to get that pointer back out to LabVIEW. And so as long as we just do something within this time frame, and this is where bugs can happen, though. If we do something within this time frame, that's fine. If we try and then use this out here after C has freed it, we're going to get crashes. Yeah, exactly that. It's where you have to be. That's the downside to the way I've done it, is you just have to be aware of that. I've designed my APIs in a way to try and do that, but there's no automatic way of handling that case in LabVIEW. You have to, it comes to programmer discipline to do that, which I don't like relying on.
Can I just say another way to do it is LabVIEW has DLL itself. LabVIEW.exe has functions for allocating and deallocating array. And then you can use that to get a pointer, pass it into your DLL, and then control it, but in the C way from LabVIEW.
Yep, exactly that. That's the thing that I didn't go as far as experimenting with, because as I say, in the first case, I had to do it this way, and then it didn't seem worth something new. But that is the opposite. So I've done it where C is managing everything. You can flip that on its head, and you
Question,
can.
do you write? Are you in charge? You control the C code?
Yeah, yeah.
That's different. So I'm usually wrapping a DLL that pre-exists, like SQLite or something.
Yeah, yeah.
Or very like 3 or 4 other things. And so I can't change it. And so whichever way they've chosen to do it, I have to match to. So you really learn a lot of different techniques because you have to, because they're all slightly different.
Yeah, yeah, yeah. And is it pointers to pointers and things like that?
Oh yeah. Pointers to pointers.
Is all fun. It did start to make sense why they do that once I did more of the C code myself. I was pleased. That's now I understand what they're trying to do. I'm not saying it's good, but I understand why.
Then there's a further issue that how do you do it in the most efficient way, like avoiding copying?
Yeah.
Which is another level.
Yeah, and so that's the obvious flaw. The other obvious flaw to the way that I've done it is it does involve essentially copying data from LabVIEW's memory to C's memory if there's a lot of data transfer between the two. So I didn't dig into it because that wasn't a concern for me. Like I say, in the performance code, actually it never really went back to LabVIEW. In the other code, we had loads of performance headroom, so it didn't matter. But I think
do it, but it's an extra level of understanding both memories on both sides and what it's doing.
Yeah, so exactly that. You can compile your C code against the LabVIEW runtime so that you can call LabVIEW memory management functions from within the C code.
You don't even need to do that. You can have LabVIEW pass a pointer to a LabVIEW structure and have it work on it as if it's a C structure. But you've got to make sure that LabVIEW doesn't try and change it while the C. I mean, you really got to understand when things happen. And since LabVIEW is designed so you don't have to worry about memory, that's the problem, because now you have to understand exactly what LabVIEW is doing with the memory.
Yeah, you have to have some concept of the scope of that. So I think that there is another level. That's the best way to describe it. There's another level to what you can do with this. I didn't go there. And it's worth saying what could go wrong. This is quite an easy list. We've already said crashes is the big one. These tend to be because either a pointer is invalid, i.e. maybe you've never allocated it and it's just a 0 and you try and do something with it, or the pointer has already been freed and you try and use it again. So that's called a use after free. The upside to these, although they are fairly common and very annoying and very unusual for LabVIEW because it's a flat out crash. It's not there was an error. Because I find these tend to be show up in testing fairly well. I'm not going to say they always do, but often it's a misconfigured node or it's a sequencing error, and they tend to be pretty repeatable. So once you see one, you can test for it and work around it. They don't tend to be the sort of thing that turns up once in a blue moon. They can be, don't get me wrong. They definitely could be. But my experience with this method is they show themselves fairly quick. Memory leaks is a big one. Like, as we said, memory is the problem. Managing between these two systems, there are profiling tools obviously for the memory over time, and it's just a case of keeping an eye on that. And it's worth saying, especially if you're looking for performance, by the way, if we're doing these additional copies and things, then you might not get the performance benefit you want anyway. So I wouldn't go to this, if C is going to be, I'm making up numbers here, but 10% faster than LabVIEW, it's probably not going to be worth the trouble, because now you've got 2 code bases to manage. You've got these additional copies that are going to take some of that performance. They're going to increase the memory usage. You really want to be going to this when you're going to be seeing a significant benefit.
James, one question. Regarding the memory leaks, do you know if the desktop execution trace toolkit can detect those type of leaks or not?
I'm 90% sure it can't, because it will see leaks tied to like the LabVIEW memory management system. So I think because you're working outside the scope of that, I expect it won't. Although I'm not 100% sure, but
You haven't tried it. You haven't tried it.
I haven't tried it, but I'm fairly sure it wouldn't.
Okay.
I should say actually.
If you try it, I would appreciate that you tell me.
I'll have a quick look because I have got a bit of test code. So actually, with the memory leaks, one of the things I did. Let me see if I can.
Because you're talking about like a static leak here. So something tells me that yes, and something tells me that not. So that's why I am asking, to see your experience in that. No?
Yeah. I would be very surprised if it did.
Yes, me too.
What I have got here is
it's like a service, no? So it connects like to the LabVIEW, so you never know what's going on there.
I'm going to assume no one wants to look at the Rust code that I also have on this VM because I might break it. So here we go. This was my test of have I got any memory leaks? Have I screwed something up? Just run this as fast as possible, and then obviously it would crash or be very apparent very quickly if we've got a memory leak. So let me desktop execution.
This is like a live demo here, no?
Yep, this is bring the whole pack of cards down.
Very cool. Thank you very much, James. I really appreciate this. Huh?
No worries. Let's see if I can get it working. So
we should bet a beer or something like that for the next CLA summit, no?
Let me see which version we're in.
Can I quickly just show a DLL something that I've got?
Yeah, go for it.
Can I share the screen while you're getting that working?
Oh yeah, perfect. Let's do that. Where's my stop gone? VMware's hiding it. There we go.
So this is actually a call in the SQLite library that I have, and it shows some of the, I'm calling DLLs, and I like to show names like I showed before so you can actually see things. And this is sort of the example of the kind of like detailed stuff you have to do to learn how to use a library. So here I've actually got a pointer to the thing I want, which is a string. But I can't really get it there because I don't know how big it is. So I can't really, it gives me a pointer to it, but I need to know how big it is. So then I have to make a call to get the number of bytes in the thing. And then I have something called move block. Move block is part of LabVIEW.exe. So if I open this, you see this is part of LabVIEW itself. LabVIEW has DLL functions.
Yes, yeah.
And this is called move block, which is very useful as a sort of Swiss Army knife of getting the last bit of functionality from a library. So here I said move block from the source pointer to my destination U8 array, just the empty U8 array. And it's configured to pre-configure this for the number of bytes. And then I convert that into a string.
So you are using like the LabVIEW memory manager there or something like that, or what?
No, there's not a LabVIEW memory manager. LabVIEW just has some actual built-in functions. If you look at it, move block copies from one thing to another, but just like C does. And then there's a couple of, I forgot, there are ways of assigning memory outside the LabVIEW memory manager and destroying it. So
okay, so you're like using that memory functions in LabVIEW, but they are running in C, something like that.
They're C-like. They're not in the LabVIEW memory manager. So they're a Swiss Army knife that lets you actually get around problems, a lot of problems. Like another problem in other libraries is they often have an array of pointers to strings. And so you can't easily take that into a LabVIEW structure, but you can get an array of numbers, each one is a pointer, and then go through on move block individually and get the strings. So there's lots and lots of tricks. It's almost a whole area of expertise in and of itself.
That is a super.
I've gotten work because I can say I know how to wrap a DLL better than most people.
That is the LabVIEWExe, what you're pointing
LabVIEWExe, yeah. If you point to the LabVIEWExe, you just put in LabVIEW, and then there's a bunch of functions you can use. Most of them I haven't used, but the memory manager functions I have used. Don't know what most of these are.
Wow, I didn't know that. Okay, thank you very much.
That's AZ. It's called AZ create pointer or something.
Yeah, so those are the ones that I think you could call from C to start leveraging LabVIEW's management more, I think, but yeah, like I said, I've not got into it at all.
I've only used it from the LabVIEWs. I've only wrapped DLLs that pre-exist that I can't myself modify. So I've learned a lot of the tricks to get around the weird things that each DLL has. So you really understand the difference between a LabVIEW string and a C string, because it really matters. You know, a LabVIEW string has 4 bytes at the front, which is the length, and a C string has a 0 byte at the end. And so they're fundamentally different. And you really have to understand how to deal with them. And so you do crash it a lot. You don't crash it a lot. That was a really well written DLL. It's really simple. Anyway,
cool, right. I think this is ready to crash. Let's see.
Do you have the possibility only to leak once to detect it before it crashes?
Oh, good question.
Maybe put a breakpoint. Just run it once, no?
I'll tell you what, I'll do it differently than I was thinking. We'll just not run that in the first case, and then we'll do the full crash. I want to see it. I want to see it really go now, but oh no, sorry. So 0, do nothing, default, free it. So this will just leak once. So let's see. So I've got this running. Actually, I need to check. You know what I didn't check is, let's put all the memory stuff on. Now I think it'd be interesting to see if this shows anything, because again, this is happening in C. Let's see what it does. So I'm going to run this just for a second. I should have got the front panel up first. So I guess that's nothing. I think I couldn't find. Does anyone remember where the palette is? I thought you could generate a marker here somewhere.
There is. It's
just so I could believe it.
Maybe in the it's. I don't know if it's in the VI in the application.
When you run it, it should have showed something.
Should have showed something. What's it?
Yeah.
Oh, hang on. Project.
Yeah.
Right. Let's try that again. Here we go. So it's showing the sub-VI calls. It is showing some resizes, whether that's...
It's hard to interpret that memory thing because of all the reusing stuff.
Yes,
yeah.
Maybe I think, James, that a good idea maybe is only to put the leak, just filter everything out.
But it's definitely not got the leak.
It's not.
Yeah, so we've got no leak showing on the end, which normally it would do when you stop it if you had one.
And why he's showing things?
It won't show the leak because the leak is in the DLL.
1 second.
Yeah.
Can you just put the leak? So filter everything out. Just take out the memory allocation and all of that, and just put memory leak, and that's it.
I don't think it'll work because the memory leak is.
Yes, you see, it's called reference leaks.
Reference leak is a LabVIEW thing. Yeah,
it's talking about LabVIEW references there. So let's clear that just to show it. Oh, what did I do? Did I just hit a funny set of buttons? Oh no, just copying there. There we go. So there, yeah. So it's not picking anything up. But if we can prove it's leaking, let's make my memory explode.
So it only does LabVIEW leaks, no? Let's say.
Yeah. Because it's only seeing, so LabVIEW behind the scenes is obviously has its own calls. Let me just delete that. Well, it's not going to save anyway, is it? Because it's going to die. So that's tracing. And see my memory trending up. So if I stop it before it crashes, we'll also still see nothing, but it's definitely
not doing it. So
yeah, and you can see it's not freed the memory; it's held onto it. So that's not going to go away until I close LabVIEW now.
But there you see the memory growing, so we saw it.
Yeah. And yeah, so if you get it wrong, if we let it go until it dies. I think, yeah, because it's trying to allocate memory. The memory allocation in C will crash. I think it will crash LabVIEW.
And this is a 64-bit.
Yep.
But nevertheless, he will crash. No, he will allocate.
Oh yeah.
Or what?
Still come out. It still picked it as a memory exception. I don't know what it'll do now.
How much memory you allocated? 11 gigabytes.
I've got 8 on this system. This particular one is a lower performance one. I think I've put about a couple of megabytes per loop is about what this one normally is. So yes, you can see it's sucked up nearly 5 gig now. But yeah, so it handles the memory full a little bit more gracefully. So let me do the reverse. Let's see if it'll let me do this. So if we reverse this, we try and free something which wasn't created. So the default LabVIEW object's going to have a 0 for the pointer. So C is going to try and read or write data at 0, and the OS or the runtime is going to turn around and say, no, that's not yours. You're not allowed to touch that. I think this will just flat out crash. Oh no, maybe I've got no memory anyway. Oh, so this one it'll catch. So some exceptions LabVIEW can catch depending on the level of error handling that you have enabled on the node. I just want to see it crash now. I don't know why I'm feeling sadistic. Let's remove the error check-in. Oh, I saved that. Gotta remember that. It's really trying to hold on. It's just frozen up on me now. It probably doesn't help that I now have no RAM left on this system. There we go. And that's the other side that you see with DLL development. LabVIEW just disappears from existence. So it's can be a frustrating process. And yeah, as James says, I definitely recommend it is easier if you are writing the code rather than depending on something that someone's provided for C, because there's so many different conventions and things like that, and they won't necessarily play nice with LabVIEW. So I've just put a couple of links on here. One is call a DLL from LabVIEW DevZone article on ni.com. That links to a bunch of other articles talking about it. The code some of the code I just showed you was from when I was looking at this. I did a quick POC just to prove it would work from Rust. So there's code there for the Rust side and the LabVIEW side just to prove out how this works. That is yeah, I'll just on GitHub if you want to have a look at it. So thank you, everybody. Let me stop my screen.